Right, so we've been given 1.5 moles of hydrogen gas. Let's just go straight into putting this into a bit of a rice table. I'm going to write out the balanced equation. And I'm going to say we were given 1.5. That's my initial. And initial consumed equilibrium. And then volume and concentration. So, and then we've been given 1 mole of oxygen, and they were put into a 200 centimeters, so it's 0.2, 0.2, and 0.2. And then they've given me a temperature over here, and then it's sealed, and we've got an equilibrium. And analysis of equilibrium shows that we have got a certain number of grams of oxygen. So we're going to put that in, and we're going to do a separate little calculation for that. And I'm going to go, number of moles is equal to mass over molar mass, and that's equal to 12,8 divided by 32, because oxygen's O2, and I get 0,4. So I'm going to say at equilibrium I've got 0,4 moles of oxygen, and then 0,12 moles of hydrogen was used up to reach equilibrium. So that means that I can say 1,5 minus 1,2, and I land up with 0,3. And remember that the consumed of the reactants has a link with the produced of the product. So it's 2 is to 1 is to 2, as 1,2 is to 0,6 is to 1,2, which makes sense because 1 minus 0,6 does equal 0,4, which is what we've just calculated. And then we need to get a concentration of each of those, and so you can say that it is that divided by that, that divided by that, and that divided by that, which is going to turn out to be 1,5, 2, and 3. They then asked me specific questions, so it calculates the concentration of oxygen gas once equilibrium has been reached, so that's going to be 2 moles per cubic decimeter. Determine the concentrations of the hydrogen gas and water vapor when equilibrium was reached, and so your concentrations there are 1,5 and 6 respectively. And then calculate the equilibrium constant, so we need the expression for the equilibrium constant, Kc is equal to concentration of products over the concentration of the reactants, and then that is going to be equal to, when I substitute, 6 squared over 1,5 squared 2, and that's going to be equal to 8. And then state Le Chatelier's principle. So we're going to have, if a system is at equilibrium and it's disturbed by stress, the system will adjust the equilibrium position so as to minimize that stress. When the pressure on the container decreased at a constant temperature, what effect would it have on the amount of O2? And we're going to have to explain it. So I'm going to just explain it first because I find that a little bit easier to do. I'm going to say I've got 3 gas moles going to 2 gas moles. So when I decrease pressure, favors less gas moles, which is reverse. So therefore, what will the effect be on the amount of O2? If it's favoring the reverse, it will land up increasing. When the concentration of O2 is increased, the equilibrium is re-established, and what is the effect on Kc? The temperature remains constant, right? Only increase, decrease, or stays the same. Kc will stay the same because it is only temperature that makes any change to Kc at all. Ethanol is produced synthetically by reacting excess carbon monoxide with hydrogen. The equation for the reaction is given. Study the graph below and find out the concentration of these gases varies during the process. And what can we see? We can see hydrogen's decreasing, carbon monoxide is decreasing, so we're using those up and we're making more and more methanol. How long to the nearest second does it take the system to reach chemical equilibrium? I've only got a horizontal line at approximately that point over there. So I'm going to go with 8 or 9 seconds. It's definitely not 7 seconds. It's not 7.5 seconds. There's still change occurring over there. And it's not 10 seconds. We've got a flat line before 10. So it's going to, I would like 8 or 9 seconds. And then if the temperature of the reaction vessel was increased at 25 seconds, what changes would be measured in the concentration of all three species? And what is going to happen is if I increase the temperature, I am going to favor reverse, because this is a exothermic reaction, so an increase in temperature would favor the reverse. So I would see an increase in the concentration of CO, an increase in the concentration of H2, and a decrease in the concentration of CH3OH. Copper is widely used to make electrochemical wiring and other applications. In electrical conductivity, crude copper is not suitable, so we need to try and purify it. Pure copper is achieved by the electrolysis of impure copper as indicated in this diagram. And impure copper are connected to the anode, and the thin sheets of pure copper serve as the cathode. The voltage across the cell is varied, and it's going to oxidize more readily than water. So there's our stuff. Let's see what we're going to do with those questions. Use the information and the conditions needed for the electrolysis of copper when answering these questions. So copper, these are in the electrolyte, that's your voltage, temperature, and the current efficiency. Which electrode of the cell at which reduction occurs? Answer: anode or cathode. Reduction always occurs at the cathode. Which electrode increases in mass due to a pure copper deposit whilst the cell operates? Well, we just said that the pure copper is being deposited on the cathode. That was in the previous blurb. Write a half-cell reaction for your answer of 7.1.2. So the Cu2 plus ions are coming across, they are gaining electrons, and they are going to become copper metal. Write a symbol of any one of the ions that carry current through the solution, and you could have chosen any one of those ions. That would have been absolutely acceptable. Write at which electrode are electrons being released by the atoms. So in other words, where is a loss of electrons? And a loss of electrons is oxidation. And where does oxidation take place? At the anode. Use the relative oxidizing abilities of copper and silver in the table of reduction tables. So looking at the table over there, we can see that copper is more likely to be oxidized and silver is more likely to be reduced. So copper is more readily oxidized than silver, which is the reason why the silver will remain undissolved. Give one reason why a raised temperature is used by industry to increase the rate. And explain why the concentration of copper ions in the electrolyte does not change, because as fast as we're making copper on the one electrode, we are using copper on the other electrode. So it is being oxidized and reduced at the same rate. Then there's a story about copper theft over here, and how would an interrupted electricity supply due to cable theft in South Africa contribute to increasing carbon dioxide emissions in the atmosphere? We would need to make more copper. Making copper uses electricity. Electricity production in South Africa uses coal, and coal plus oxygen gives more CO2. So that's how we increase the CO2 emissions. A company sets up the apparatus represented below to simultaneously electroplate metal rods with zinc, silver, and nickel. Will the items to be electroplated be situated at the anode or at the cathode? Well, in each case, you're going to have the cathode is where you're going to deposit the new metal, because the cathode is where you're going to make reduction is going to take place, and you're going to create metals. So you're going to have the iron, you're going to gain electrons, and you're going to create the metal. So that's going to happen at the cathode. Give a formula for a suitable electrolyte that could be used in the cell where silver is. Remember, I've told you always tell me the nitrate. So in this case, I'm going with silver nitrate. Write a half reaction equation for the reaction that occurs at the anode in the cell where the zinc is electroplated. So zinc is going to become Zn2 plus 2 electrons. So that's where you're breaking up the impure zinc ions to make new ones. While connected to the circuit above, 11,8 grams of nickel are electroplated onto the metal in 1 hour. How many moles of nickel is that? So the first thing is that is going to be number of moles is equal to mass over molar mass, which is equal to 11,8 divided by 59, which equals 0,2 moles. And then we are going to say what mass of silver metal would be deposited on a similar rod placed in the silver electrolytic cell. So I'm going to take those. Remember that for every 1 electron, for nickel it's Ni2 plus, whilst for silver it's only Ag plus. So therefore the number of moles is going to be double the 0,2, because we are going to have twice as many silver ions for the same number of electrons as we would have had for nickel, because nickel needs 2 electrons every time, while silver only needs 1 electron. So we're going to have 0,4 moles, and then you're going to say that mass is equal to number of moles times molar mass, and that's 0,4 times the molar mass of silver, and we land up with 43,2 grams. An electrochemical cell is represented, and this is very much bookwork. What energy conversion takes place? We're going from chemical to electrical. Define the term oxidizing agent. It is a substance that causes another one to lose electrons, or you can say it gains electrons itself, or causes electrons to be lost. Write down the anode half reaction. You've got your cell. And we can quite clearly see that aluminium goes backwards and that goes forward, the silver goes forwards. So the aluminium is going to get oxidized, and therefore it is going to be at the anode, and this will be your cathode. And so you're going to first write down Al goes to Al3 plus 3 electrons. I'm going to write down that I just wrote that backwards, so I'm going to change its sign, 1,66 positive. The next one, write down the cathode half reaction. The silver, it's just 1 plus. The silver plus an electron becomes silver metal. This one I've written in the normal direction, so I add those together. I'm going to find that my cell is going to turn to be 2,46 volts. And then I need to write the overall cell reaction, I need to multiply this by 3 by 3 by 3, and it becomes Al plus 3Ag plus becomes Al3 plus 3 Ags. And then if 0,5 moles of electrons flow from one electrode to the other, calculate the change in mass that occurs at the cathode. And so we're going to, the cathode is going to be over here, it's going to be your silver, and you're going to simply say 0,5 moles of silver, because each silver requires 1 electron, so it's easy as that, and you get 54 grams. Study the substances below and select one that meets each criteria. Consists of polar covalent molecules. So covalent means it has to be a metal and at least 2 nonmetals. Non-metals, non-metals, non-metal. There's no bond over here. This is non-polar covalent because it's your typical tetrahedral shape. And we know from organic now that it's non-polar as well. So the only one that's polar covalent is water. In the solid and the liquid phase, we get hydrogen bonding. Oh goody, look at that, it's water again. A solid allotrope comprises of an atomic lattice of covalently bonded Atoms, your allotropes are carbon, you've got graphite, you've got diamond. Remember, allotropes are all the same phase but different atomic arrangement. Dissociates into ions in solution. Only potassium chloride is ionic and conducts electricity when melted into a liquid but cannot conduct as a solid. Only ionic substances have that characteristic again. Alongside is a graph that shows the boiling point of various hydrides. Hydrogen fluoride, ammonia, and water have much higher boiling points, and this was in your previous paper, so you should have really got this clear. This is due to hydrogen bonding. Briefly explain what the properties are of those three that cause the anomaly. You can't just tell me that there is an anomaly, I can see that. Also explain how those properties result in such a strong intermolecular force between the properties. So the first thing is that the NOF gases are small. Atoms pack close, strong IMF. NOF gases, high electronegativity, therefore polar, or should we go very polar, therefore strong IMF. And then define electronegativity. Oh my word, if we see that one more time, it is the tendency of an atom to attract a shared electron pair in a bond. Referring to the electronegativity difference, explain the polarity of the bond in oxygen. So the EN difference is 0, therefore nonpolar. Or you can say electrons evenly shared, something like that. What specific type of intermolecular force would hold an oxygen molecule lattice together? Nonpolar molecules are held together by London forces or instantaneous dipoles. And in terms of intermolecular forces, explain why oxygen has such a low boiling point, because they are very weak intermolecular forces, therefore particles move apart easily.